Okay, let's start, everyone. Good evening. I guess an awkward time for a lecture, but um, hopefully you have had your dinner. Um, but in any case, want to welcome you to 202A, also known as CS 213A, but usually we don't get a whole lot of CS people. So I'm going to spend some time going over the course logistics and just a very high level sense of what the course is about, and then we'll go into kind of the first lecture. So some information about me. I'm both in CS and ECE department. My office hours are going to be, actually this is wrong. Ignore this. It's Monday and Friday, so we'll correct the slides. Actually, let me correct it on the fly. Monday 2 to 3, Friday 4 to 5:30. Okay, so it's corrected now. Office hours are in my office in this building. And generally speaking, since we are using Piazza, I'm going to talk more about it. I think it's better if you just message there. You can send me a private note if necessary. If you do send me an email, put the course number in the subject line. My assistant, Lorena, in case you're trying to trace me down, then maybe she can help, but you probably won't need her. There's no TA for the course, but some of my students and postdoc are going to help out in various roles during the course, so you are going to encounter them as well. I'm pretty responsive electronically, and also I realize that no office hour works for everyone, so I rely quite a bit on Zoom also. Hopefully some of you have used it. It's kind of like Skype, so if necessary you can always kind of arrange for a Zoom meeting, and that way there are a lot more options that open up, even when, for example, I'm on travel and occasionally on weekends or late evenings and things like that. No one is enrolled in the course yet, as all of you know, and part of the reason is that we do have a because I kind of out of my own resources support the course projects, which tend to get sort of costly in terms of what we do. Department sort of doesn't support the projects directly, so there's a limit of 30, as well as kind of just being able to supervise and mentor the projects. So what you need to do, hopefully, if you are on the waiting list, you would have received an email from me with kind of a link to this web form. Anyone on the waiting list and didn't get an email from me? Okay. If you are not on the waiting list and are here, then you can grab that QR code and fill out the form. There are 56 students on the waiting list. I don't think there are 56 students here from the look of it. But in any case, by the time week 2 arrives, sort of most of the students disappear anyway. So almost everyone who's interested. Yeah, anyone who's interested in getting into the course typically gets in. Part of the reason we go through this song and dance in effect is, unfortunately, in the UCLA system, students over-enroll and then drop out, and that leaves the courses in a weird situation. So this kind of forces a decision on you, and I'm going to use the information there to prioritize. And loosely speaking, the prioritization is that PhDs get priority over MS, over bachelor, undergrad, that order, and students in CES area and computer science get priority over other areas, and then they get priority over other departments. I this form asks questions about your background in embedded systems and all. To the first order, that's not a consideration, because of course if you already know about embedded systems, then why would you need this course? But of course, if I feel that your background is not up to it, then I will deprioritize. I'll give you lower priority, and also I give priority to those who are engaged in research groups in this space. Okay, just because those students tend to need this material. But in any case, I want to have a diverse class with sort of diverse background. So. And if you make a strong case, I'll welcome you. Again, the limit of 30 is not a hard limit either. Like I said, it's really arriving from that I support the projects out of my own research funds and sometimes out of my own pocket. And also there's no TA, so that kind of places a limit as well. Any questions? Okay. So, at a very high level, what this course is really about is a confluence of a few different technologies which collectively sort of come up to create systems which interact with the physical world. And the four technologies are kind of devices that are sort of resource constrained, so we wear them or they're in our spaces around us, or also in future perhaps inside us or inside animals and whatnot. Devices that we carry, mobile phones and such, kind of networking technologies which allow communication pretty much in a pervasive manner now, and every day we keep hearing kind of new ones. Like just a few days early, when Amazon announced its new set of devices, they announced this sidewalk network, which is essentially kind of like the mile around your home kind of network, so that your dogs can communicate back to your home and stuff like that. And then cloud services. These devices by themselves are, because they are resource limited, they can't really sort of do a whole lot of intelligent stuff by themselves. And that aside, kind of so much of interesting stuff happens when things talk to each other. So sort of network and cloud services play a very important role. And based on this, kind of the variety of sort of types of systems that all, loosely speaking, end up being about interacting with physical systems, interacting with things and humans and animals and whatnot in that space. A term which is often used is Internet of Things. So embedded computing is a pretty old term from 70s, 80s, and I think every few years kind of some new spin on that comes. I think Internet of Things is currently one in vogue. But what happens in these systems is that you can kind of think of them as they collect data, so they measure things, then they apply algorithms to make some sort of inferences from it about what's going on, what's the state of the world, and then kind of they close the loop by interacting with them in the reverse direction, so controlling things, nudging behaviors, sort of just that loop gets closed. And of course, these kind of systems have existed forever, right? I mean, even our good old sort of appliances and all, toasters and microwave ovens and all are examples of embedded systems. But they were super simple, and I think the complexity of these things, the richness of behaviors they exhibit, and the fact that they're interconnected and they can talk from afar and all those things have happened in recent years. And so they have begun to impact a whole bunch of application domains. Health is a big application area. I mean, you see them in the form of these Fitbits and Apple Watches and whatnot. Medical researchers make use of them. Buildings, sort of making them more sustainable, safer, smarter, more comfortable. Transportation systems, security systems, as in sort of police and military and stuff like that, entertainment, and kind of the list goes on, where these systems are getting used. So I guess diving a bit deeper, so the course was created many years ago. It's called Embedded Systems, and I've not resisted the temptation to call it something catchier. So we still call it embedded systems because, in a way, that's the more foundational term. Embedded systems are computers which perform some sort of dedicated functionality in context of a larger system, or a larger mechanical system, or a larger electrical, biological, some sort of system, and often have constraints, physical constraints. So I took the Wikipedia definition, which calls it real-time computing constraints, but think of it more generally that constraints which comes from physics. So it's not simply about timeliness, although that's a very important one, because if you're interacting with physical things, then you have to keep up with it, because unlike a human where you might wait for a spinning cursor, the physics of moving car will just happen according to the physical laws. So there's very little laxity in this. So correctness in these systems often depends also on being timely. But it's not simply about time increase, it's also about location. Doing these systems doing their action in a wrong place is useless. Power, if they sort of, or rather energy. So these are they're all sort of constraints that come in these systems, which to the first order are not that critical to functionality in traditional sort of computing. So general purpose computers are designed to be kind of jack of all trades, cater to do a wide range of things, and embedded computing systems tend to be more focused. So what are examples of embedded systems? I've kind of already alluded to some of them as we went along, but like a pacemaker, autonomous driving unit like the autopilot in the Teslas, or the computer inside the projector up on the ceiling. These are all examples, and of course it's kind of a spectrum. It's very hard to say that I mean, if I look at my laptop, certainly it has some attributes of embedded systems. Increasingly these things have sensors, and also oftentimes devices don't really fall very cleanly, so they have attributes of being embedded in some regards and being general purpose in other. What are the real-time constraints? Very loosely speaking, there are two types of real-time constraints that systems face. One is that they capture data at a certain rate, and so the processing has to keep up with it. Okay, because if you fall behind, so for example, if you're sampling whatever, if you have a camera observing the scene and it's sending capturing data with certain amount of pixels and a certain frame rate, you just have to keep up with it, because if there is a mismatch, then you'll basically have to drop the frames. So that's a bandwidth constraint. And the other one is a response time constraint. Some stimulus, something happens from the physical world, and you have to respond back sufficiently fast. So pacemaker detects a problem in the heartbeat, and it has to respond within a certain time. So latency and throughput, these are very loosely speaking constraints that come into play. In some cases, there is absolutely no laxity in this thing. That is, if you miss, the system is essentially failed, in which case the term which is often used is hard real time. But most systems are not entirely hard real time. There is some degree of slack that does exist, and so the alternative, the other term which is used is soft real times. So as I mentioned, besides real time, besides the time issue, the other physical attributes, and location and power or energy are two other examples of physical attributes, physical variables that play an important role in embedded systems. So if you look at power and energy, I mean, there's obviously the issue of battery life, right? You want it to make sure the battery lasts sufficiently long. But what are other aspects of power or energy that you can think of that might impose constraints? Anyone? So, heat. Yeah, so you don't want it to become too hot or start burning you, or if it's an implant inside your body, then that heat has to go someplace, right? So one issue is it can damage the environment, right? The other thing is it can damage itself. I mean, too hot, it basically begins to degrade the electronics. Electronics age more rapidly if there's too much heat. Also, in modern systems, if they heat, to prevent damage to themselves, they throttle themselves down. So if it heats up and you have not designed the thing properly, then it will become slower. Okay, so you will start seeing deadline misses, for example. It will fail to keep up with the performance. So heat is one. I talked about battery life. Can you think of something else?
Memory constraint.
No, I'm talking about energy power related.
So uniform supply. Uniform supply. Like if you're using something like a solar device or something, it might not have the same energy level throughout.
Yeah. Okay. Right. So I'm going to rephrase it. So power has to come from someplace, right? And so when you are drawing energy, then you're drawing it at a certain rate, and so the supply system need to be able to supply that current. And oftentimes there is a mismatch associated with that, because so it's not simply how much power, how much energy you are using for a particular task, but also the rate at which you are drawing the current. So, for example, if you have a system which is making use of some particular source, it may have a lot of energy, but maybe it cannot supply the current necessary. So energy is integral, right? So you can have limits on both kind of how much energy you need and what rate you are kind of drawing things from. So current often becomes an issue, not just in kind of low power systems and all, but also it can be in plugged in systems and all, right? I mean, you cannot draw an arbitrary amount of current from an outlet either, right? So there is a limit that you face there as well. Can you think of other type of physical constraints now? So we talked about energy, we talked about time. Location is another one. I mean, if a robot is supposed to do some physical thing, if it does it at the wrong place, then of course you have a huge problem. Can you think of any other physical variable that embedded systems need to? Size, yeah, volume, weight, right? These kind of things. I mean, you don't want, let's say those hearing aids or stuff like that, right? I mean, those are great examples, and oftentimes these things couple, right? Smaller the size, it begins to affect the battery and so on and so forth, okay, or it begins to affect how fast a processor you can put. So these constraints are not independent either. So main trends in these systems, they're getting networked. That obviously has been a huge thing in the past 15-20 years. Getting smaller, coupling with humans in variety of ways. I mean, the wearables and implantables and stuff like that. What I've called as AI enabled. I mean, increasingly these are not simply you press a button and the toaster pops up. There's a lot more intelligent processing going on inside these things. So you have specialized chips and all which have begun to emerge, and which do neural networks and all in these tiny little things. Multi-tenant, that basically is a jargon which refers to the fact that instead of a single application running on those devices, they often have multiple things sharing that. So this is we have always used to multiple applications running on our laptops and all, but if you think about what happened to our phones, right? Phones used to be just phones. But now phone is just one of the phone app is just one of the app of gazillion apps on your device, right? But the same thing is happening in all sort of embedded devices. The drones started out just as drones, but now there are app stores for drones, app store for watches, stuff like that. So multi-tenancy refers to the fact that this desire to do multiple things sort of cause stuff there. Privacy issues, I mean, all this data kind of flowing and all, and associated security issues. When bad things happen to these devices, it's not simply a file containing your SSN getting stolen or stuff like that. Now it can have real physical consequences of from a privacy perspective. They're capturing much more intimate data, right? Sensors on you, around you, and whatnot, as well as since they take physical actions. So if they get hacked, they have, I mean, someone hacking into some system of your car can have far more consequences than just someone hacking into your laptop. So this course, loosely speaking, is about embedded systems that have all these characteristics, but particularly ones which are networked. Okay, there's a pretty photos out here. I'm going to skip those, but our world abounds with these kind of devices. And if you simply look in terms of what's been happening in computing in recent, I guess, decade, let's say, is that we kind of moved away from general purpose computing to kind of these two ends really where the action has been happening. The cloud, big data centers and stuff like that, and then the edges. I mean, we essentially, each one of us have potentially tens of these devices, and our laptops, desktops have been kind of reasonably stationary by comparison. So in terms of how many computers per human being, we kind of crossed that ratio many years ago, and that keeps increasing. The car you drive probably has 100 plus processors of some form or the other. So most computers are embedded at this point. Anyway. Now, variety of related jargons and terms, and also I also wanted to kind of describe a little bit. So one term you will we hear a lot is Internet of Things, and it's basically this concept that at some point the internet became less about traditional computers and more about computers which are inside things. So with some derision in computer science, we often refer to as IP to the light bulb, IP standing for the Internet Protocol. But this notion, like if you go through papers in computer science and all, this view that, hey, I want to control my light bulb that's been around for long. Of course, it became reality some years ago. But essentially everything, networking everything. Early stuff was like people were, if you go back to 90s and all, people were putting their coffee makers on the internet, stuff like that and all, and now that's sort of pretty routine. So the challenge which came with this thing, of course, was the internet was never designed for that. Your original IP address space was 32 bits, and that means 4 gig, which is not even enough for one computer per human being, and now we're talking about tens and hundreds. So that in part caused the migration to IPv6 so that we have a larger address space. But that's just one of the consequences. As we begin to put these devices on the internet and we are trying to control things, then that latency became important. So I'm sure you're hearing a lot about 5G nowadays, and one of the big things in 5G is that it has very low latency. So traditionally cellular systems, cellular wireless have latencies of hundreds of milliseconds, okay? Whereas 5G talks about latencies which are a millisecond or so. So driven in huge measure because of the IoT oriented traffic. So all these consequences to both the internet architecture, the edge networks, and kind of processors and all of these things are being driven by this trend that we are facing. So again, I think rest is pretty obvious, but kind of it's basically, I guess, suffice it to say that almost every aspect of what computer scientists and electrical engineers do is being impacted by these newer class of systems. So if you look at a typical IoT system nowadays, it kind of has sort of these tiny things at the very edge, and sometimes not so tiny. I mean, a car obviously is not a tiny thing, but some sort of an edge device. And by edge device, by kind of, you can think of it as something which has the sensors and the actuators which is causing it to interact with the physical world. Then it talks to the internet somehow, and oftentimes these things are so resource constrained that they cannot have the necessary communication interfaces to directly talk to the internet. Okay, they are too resource limited even to have a Wi-Fi chip on them. So oftentimes you would see some sort of a gateway device, either kind of some dedicated gateway or your smartphone or PC acting as that gateway, and in some cases, obviously, they can directly talk. So cars have cellular radios, and they can kind of directly talk. Sometimes these devices, instead of directly talking to the gateway, they may have what is called as a mesh network, which they talk among each other and kind of route the packet through that mesh before hitting the gateway. So all sort of networking scenarios kind of exist, but somehow you sort of eventually get to the internet. So within the bubble out here, there might be all sort of private addresses and all, and so like for example, your Fitbit talking to smartphone over Bluetooth link doesn't have an IP address of its own, but still reachable because some app on the gateway helps proxy it on its behalf. So somehow through some magic of layering software and all, you kind of manage to reach things. Fitbit can still reach out and update the firmware out here and all because their app takes care of hiding that. Another area which sort of often, a term which is often used for these systems is ubiquitous computing and pervasive computing. And this is more, I guess, the term ubiquitous computing and pervasive computing have been around in computer science for a long while, but they didn't get the same, even though they refer to the same category of systems, but they never crossed they never became popularized, even though there are conferences and all and journals and all. So it's kind of, these are more academic terms, but it's basically this notion that is computing everywhere, computing just pervading everything. Okay, that's basically kind of the idea. Back in 1980s, the famous Xerox PARC lab kind of did a lot of work in this space. So some of the early papers in this space kind of came from there. But of course, this space is all around us. So in fact, one of the most prominent conferences which deals with these kind of systems is something called UbiComp, UBICOMP, stands for Ubiquitous Computing, organized by ACM, which is the main computing society. So I mentioned that because when you look for project ideas and all, then that's a great source for inspiration. Another term that gets used quite a bit is called cyber physical systems. And it's a term which came more from people who were working in control systems. So like Professor Paulo Taboada, his lab out here is called the Sci-Fi Lab, CYPHY. But essentially the notion in cyber physical systems is that these are computers which interact with the physical world, which is pretty much the definition that we are using all along for embedded computing also. Part of the notion, so there's some sort of a loop out here, as shown in this slide. There's some physical world out there, there's sensors, and then we kind of go through some sort of the cycle of making some inferences about what the state is of the physical world, and then making some decisions, and then driving some actuators. Okay, so kind of a typical control system. And what people who are working in, who started out from the CPS side, emphasized was that if you are reasoning about whether your program is buggy or not, let's say, okay, you can't just think of it in isolation. You have to think of it together with the physical world that it is interacting with. So normally when we think about bugs in a program and all, then it's, if you're dealing with files and all, then it's all virtual bits. But if you are trying to reason about whether this program is buggy or not, and if it is driving up, let's say, the MCAS system in Boeing's ill-fated 737 MAX, that's a great example. You can't talk about the program being buggy or not independent of the physics of the plane and the humans in there. In fact, just this week, last Friday, NSTB said that Boeing should be testing it with the average pilot and not the test pilots. And that goes on to show that the same program with a different set of configurations is buggy and versus not. So those kind of issues sort of come up as well. So CPS people kind of started out by focusing that how can I model a software and a physical thing working together. The software is described in terms of state machines and kind of things we study in digital logic courses and programming language courses, whereas the physical world is in terms of differential equations and all. And human beings, how will you model human beings? What field lets us do that?
AI.
No, AI is artificial. It's not about human. Cognitive sciences, psychology, sociology, right? So in fact, if you have a disdain for humanities, get rid of it, because increasingly you have to model humans and their behaviors, and also they provide the necessary theories to be able to model that component of the system. So that leads me to this next point, which is it's not just.
Sorry.
Go ahead.
Just one thing. So, just adding the sensors and actuators, is that the thing that makes it different from ubiquitous in computing, or just like a previous
I guess in ubiquitous computing, the actuators were not there. So most of the time they were focusing on the one-way traffic, and now. Even that's a bit of a misnomer. The way I like to think of it is, it's not as if you collect the data just for enjoyment, right? I mean, you always do something with it. The question was, what did we do with it? Okay. So in ubiquitous computing and all that data and the inferences you made for it, they were used for some slow time scale human decision making. Maybe that will affect the medicine the doctor prescribed to you, or maybe it will affect your decision to buy a more efficient machine or stuff like that. So they were longer time scale decisions. Whereas CPS systems began to look at things where this loop was closed much more rapidly. Okay, but I think ultimately, if data is collected for no decision making, then it's useless data anyway. Okay, so it's really, and I kind of attempted to show it out here, which is there are nested loops, and so there are faster loops inside and slower loops outside, and I think almost every system is like that. And the pervasive UbiComp people tended to focus on that outer loop, almost like I collect the data and I kind of ponder over it and come up with a new science theory or a new decision making, whereas CPS people begin to worry about much more rapid time scale things. And roboticists always worried about it, if you think about it. So robots are a special case of CPS. But CPS certainly represents a much broader array of things. It could be traffic light control, it could be controls in your cars and planes and stuff like that. So electrical grid, these are all examples of CPS. And the point that I was making was that they are not simply CPS cyber physical, but there's also increasingly human cyber physical. So when you think about these systems, somehow we need to model the three together in many cases and factor those things in. And you face that in many cases. Obviously, cars are a great example, but also otherwise, I mean, any place you have a human operator, you kind of face that. Robotic surgery, UAVs with a human pilot, all these are examples. Now, since in engineering and CS in particular, we are fond of creating unnecessary terms, so there's another one which has come up in recent years, or several, which are very closely related themselves: edge computing, fog computing, swarm computing. There are all these kind of terms. Sometimes they come up because people just want to sound distinctive, sometimes because of a desire to have a standard. But in any case, loosely speaking, edge computing, fog computing, these kind of things are basically about the following: that for a while, IoT systems became one where we take sensor data, ship it to the cloud, something running in a data center, and then you kind of send the commands back out to the actuator. But that runs into problems of scalability, bandwidth, response time, all sort of things. So these approaches are all about extending the cloud closer to the devices which are producing and consuming the data. Okay, that's kind of sort of my way of describing that. Okay, so traditional IoT, kind of, if you look just a few years ago, this was kind of the model that we'll have these relatively dumb devices that primarily sources and sinks of the data, and everything happening in these massive data centers, but all those things of scalability, latency, security, all those sort of things. So what are edge computing and fog computing? So I just looked at Wikipedia. Edge computing they define as distributed computing paradigm, which brings computation and data storage closer to the location where it is needed to improve response times and save bandwidth. Okay, so essentially you are trying to put data center type functionality or cloud services type functionality closer to the edge, presumably in some computers which are close to your devices, maybe something at your home or in that factory or stuff like that. But that's not the only definition, as we'll see. So fog computing, they define as is an architecture that uses edge devices to carry out a substantial amount of computation, storage, communication locally and routed over the internet backbone. Kind of, so this one is saying, let's take the same thing as we have in cloud computing and push it out to the edge, and this is basically essentially trying to say the same thing. Now, unfortunately, this space is full of marketees and conflicting jargons and all. So one type of usage is, the distinction people draw is that edge computing is processing on the end devices. So like on actual your smartwatch or toaster or whatnot. And fog computing is computing done on network nodes near the end devices, so on like the routers or the home gateways and all. And there's ample support for it, and this is probably the more widespread view that exists. And the confusion really, if I go back out here, is that like if you look at the fog computing, they kind of make a reference to edge devices, but then what is an edge device? I mean, is it that router in your home LAN, or is it the device you're carrying in your hand? But in any case, so this is the view, that more prevalent view, which is I have the cloud layer, I have this fog layer, which is kind of the edge of the network, but is still viewed as part of the network infrastructure. And then finally, there is this edge layer, which is the actual devices with the sensors and actuators. Okay, but that's not the only definition. The term fog computing comes from Cisco, the big networking company, and they basically say, you don't have to read all of this. Okay, they basically say that both are the same, both do processing at the network nodes near the end devices, except they say edge computing is a general concept and fog computing is Cisco's specific standard. Okay. So that's another one. And of course, the confusion doesn't end there. There's something called Open Fog Consortium, of which Cisco is a founder, as at Princeton and a couple of other organizations. And they basically say edge computing is computation at the edge devices, but they don't define what edge devices are. And fog computing is the interconnection between that and the cloud. Okay. So anyway, I don't want you to worry about all of this, but just wanted to point out that these two terms are not very well defined, and different places use it in different ways. And Berkeley and some other places use the term swarm also. So that's the third one in the mix, which is equally nebulous. I think, again, I'll just refer back to that. Loosely speaking, this is about pushing stuff closer to the edge, but doing so in a manner which is still somehow managed. So one of the things these cloud services give us is that they are multi-tenant, you can share them, you can manage them properly and all, whereas traditionally local computing on the devices was always a fixed thing baked into your toaster and all. Okay, but now suddenly we are saying there's more a properly administered way of doing computing closer to the edge. Okay, either on the edge device or on the network nodes which are close to the edge device. So that's kind of a loose concept. So that's what these embedded systems are. Why the interest in them? So I guess I mean, if we go back to kind of the early days in 80s and 90s, the first generation of these systems happened in a couple of places. Battlefield, in a lot of these things, military tends to kind of be the leading edge, and also factory automation, sort of assembly lines and stuff like that. But those were the first generation systems. They were kind of the factory systems were all kind of wired and stuff like that. The military was perhaps more forward looking in this regard. But then in 90s, when these devices kind of hit the right size, power kind of point and all, then at that point other applications began to emerge, starting with the sciences, that if I could measure things out there in ecosystems and cities and whatnot, then we can learn about their behavior and kind of develop new science and new models, and which in turn drive new policy and all. So actually a lot of work in that first generation of systems happened here. There was a center here called SENSE, Center for Embedded Network Sensing, which was the national center on an area called wireless sensor networks. So that was this view that you have tiny sensors kind of wirelessly connected and examining or measuring things out in the world. So the focus of the center was like forests and ecosystems and lakes and rivers and monitoring for earthquakes and those kind of things. But after that, a whole bunch of other things have emerged. Certainly kind of the focus on security and defense has always been there. Health emerged. City, workplace analytics, all these kind of things emerge. As a no-shot transportation, energy grid, all of these things. But these first generation of systems were still about kind of let's get insight. Okay. What has begun to happen in recent years is that the loop begins to get closed. So it's sort of the way I kind of put it, instead of just discovering knowledge from this data, we begin to take action on it somehow. Action in a relatively small time scale, not like the knowledge dictates policy and we kind of or leads to new science, but rather on a short time scale. So for example, it could be to nudge behavior related to health, or to control a car or stuff like that. Okay, so I mean, we normally think of control systems and all obviously in terms of vehicles and stuff like that, but actually interestingly even things like mobile health and all are headed in the same direction. So if the goal is to keep you healthy, then as we continually monitor things, we could even nudge your behavior and all. Imagine someone who's trying to wean themselves off smoking. Or opioids or stuff like that, then if we can detect precursors to certain behaviors, then the system can intervene and kind of try to nudge the behavior, change the behavior. It's by giving you notifications or maybe having a caregiver intervene. These are all examples of control systems, except control systems which are now involving humans. So health systems are, mobile health is a great example of it, but there's no shortage. I mean, of course, I'm sure you have seen all those impressive displays of swarms of drones and all, but I mean, cars talking to each other and things in the city. I mean, San Diego a few weeks ago made a big splash about like how the light poles, they have smart light poles with sensors on them, and they are doing things like detecting bicyclists and stuff like that. So all sort of cool stuff is happening in these things. One of the questions that people are sort of still trying to figure out is what's the best way to run these systems. So of course they are massively distributed, but do you still think of them as a distributed system, as if each one of them is running some program and they're interacting with each other? Or can I think of them as logically centralized? Can I think of these systems as if all the data were coming to a single place, I'm running a single program and kind of controlling all of these, even though in reality it's a distributed system. So it's all about kind of getting your programming abstractions right, the software platforms, and also meeting those latency and those kind of requirements. So a lot of work happening in these kind of things. That do I really kind of, can I run these, can I implement these systems and be this kind of massively distributed, billions of devices, and I have to worry about the behavior of billions of little programs interacting with each other? Or the flip side, can I bring all the data to a central place in a logical manner and then work off them? So lots of interesting projects. This one I just lifted out of Stanford. They have a project around this concept. What people often talk about is that there's probably going to be a combination of local autonomy and which is fast, and then a logical centralized control which is slower. So imagine Amazon operating the fleet of its delivery drones. Clearly, drones would need to have some control loops closing locally. You don't want to go and hit the cloud every time there is an obstacle coming in front. And yet, you also need to manage the swarm properly, okay, because you need to route them differently and all. So there's always going to be a combination of local and kind of centralized stuff of some form. Yeah, I'm going to skip this slide. Okay, so suffice it to say, what we are seeing is kind of this sort of mushrooming of technologies around kind of this concept of these kind of systems, but they are eventually kind of playing with the same bits. I mean, there is a cloud computing component, there is various kind of networks, there is kind of mobile devices and embedded devices, and they are being sort of put together in different ways. If we kind of step back, architecturally, we can, as I pointed out earlier, we can kind of think of them as kind of 3 layers. There is kind of this set of devices which directly connect with the physics, physics of the humans. Okay, so they have the sensors, they have the actuators. Oftentimes they are resource constrained, but not always. Then there is some sort of layer which is about hooking up back to the internet, and of course then you have the internet with its cloud services and all. And so this model, some people refer to as a device gateway cloud models, kind of 3 tiers, 3-tier model. Device layer, the gateway layer is kind of, you can think of them as, this is where I'm transitioning from being part of the network, managed network, to kind of the physically coupled thing. And of course, the separation is not always very good. Like our smartphones, not only are gateways, but they also have sensors and all, right? I mean, so that separation is not necessarily clear. Yeah.
Could you give an example for implantable device?
What device? Implantable device? Okay, yeah. So, like for example, if you look at Professor Dejan Markovic's group out here, they create these electrode arrays which implant inside the brain, okay, and they do 2 types of things. They sense what the firings of the neurons, and increasingly also what is called as deep brain stimulation. They stimulate things back. And it's used partly, I guess thus far the users have been for things like dealing with epilepsy and epileptic seizures and stuff like that. But also there's some pretty cool work which is happening. My postdoc, Luis, interacts with this group, which is about people who have memory formation problems. Okay, so like, you know, we have the short-term memory, long-term memories, there are all these stuff happening. So people, I think an active area is what's called as brain prosthetics. Okay, of course that's a cutting edge. Implantables also include mundane things like pacemaker and all, mundane by today's standards. Okay, so yeah, implantables, lots of interesting possibilities there. And then there are also simpler implantables which are called subdermal. They just go under your skin. So a lot, like instead of wearing a sensor out here, what if it was a tinier sensor like a rice, a kernel of rice kind of thing, and just sitting under your skin? That's also happening now. So particularly for monitoring like blood glucose and stuff like that. So these are not deep implants, they're kind of near surface implants, but they give you 24/7 kind of thing. There are implants for eyes to measure ocular pressure, so all sort of stuff.
The EMG sensors, like also
EMG are currently surface sensors because they measure, they kind of sit on the thing, they're measuring the muscle electrical activity. Yeah. So EMGs are not implantable, but those electrode arrays that I was mentioning, they are replacement of EEGs if you think about it. So EEGs sit on the surface of your skull, and they get a signal which is a summation of the signals from a lot of neurons, but it's not very specific. If you can put an electrode right next to a neuron, then you get that neuron signal, and that's what groups like Professor Markovic's are doing. Anyone from Dejan's group? Okay, oh, okay. But it's pretty cool stuff. Okay, so in terms of the technology landscape, at this layer, a lot of action in terms of very low power processors. I'm sure some of you have at least heard of platforms like Arduino, but there's a whole bunch of stuff out there. There are a whole bunch of operating systems, languages, and all deal with this thing. This layer similarly has its own set of things. This is where you begin to get into higher end processors. Very loosely speaking, so in this IoT domain, the company which rules in a way is the company called ARM, which designs processors, and then many other companies build actual silicon chips around them. And ARM has two series of processor, M series and A series. Very loosely, this is the domain of M series processors. They are the lower power kind of stuff, okay? And this is the domain of A series processors. So when you look at like a Raspberry Pi, it has an ARM A core. Whereas if you look in Arduino, the ARM-based Arduinos, okay, then they will have a Cortex M series processor. This is where you are dealing with Linux and stuff like that, okay? This is where you are dealing with lighter weight operating systems. And then of course, there is a whole bunch of stuff happening on the cloud side also. You have AWS IoT, Azure IoT, Google IoT. They're all kind of have created these services and all. And what's happening is that things like machine learning, AI, control, these are becoming services, right? I mean, there are now services out there. You can send it an image and it will tell you whose face it is. You know, a service to which you can load sensor data and it can train a model for you. So all these cloud services which are doing some pretty creative stuff with with the data you have. And some of them have begun to do the edge computing thing that I was referring to. That is, you can do stuff there in the cloud and then you can push and run it nearer the edge. So you can now train a neural network model and then push it out onto a Raspberry Pi or even to a USB stick out there. So all these kind of things, I mean, now we are talking about stuff which has appeared in the past year or two. So very rapidly evolving area, a lot of interesting stuff happening and sort of cool to play with. Okay, I'm going to skip this. Yeah, I guess, so I already referred to that how tiny processors, there has been a lot of stuff happening there to make them lower power and yet maintain the performance. Silicon technology, as you know, has kind of plateaued. So now there is the hunt is on for the next generation. So a few weeks ago, there was this news item about MIT creating a processor using carbon nanotubes. Anyone read about it? It was kind of splashed a lot because suddenly, for the first time, someone has created a complete processor in post-silicon technology, and with solving some pretty challenging engineering problems. The processor they built is a processor called RISC-V or RISC-V, okay? And that's the open source competition to ARM. Okay, so ARM is a company, but RISC-V is a processor that UC Berkeley designed, and they've released it in the open, and then people have begun to make chips around it, and you can run Linux or other operating systems and do cool stuff with it. So I guess the point I'm really trying to make is that this open source stuff is no longer just something about software. You can actually, and you have entire open source processors also. Another enabler, I guess in some senses, is the whole maker culture. That is, you can create complete IoT devices, all aspects of it. So remember, now you can make the silicon, you can obviously do the software, but you can also do kind of the other aspects of it. So this whole kind of desktop fabrication and then rapidly getting small volumes manufactured under contract. This is what made China's Shenzhen happen, really. Okay, kind of you can go through the whole manufacturing cycle very easily, and you can literally kind of do it in your lab or if you want, even at your home if you are rich enough. So what it allows you to do is to create a working prototype very rapidly, as opposed to previously where every step of the way you'll have to deal with sort of a manufacturing chain which was pretty costly and onerous. So hardware, both electronics and mechanics, it's kind of become like software, which is you can easily rapidly iterate over this thing. So you have things like laser cutters and 3D printer and PCB milling and soldering machines and stuff like that. UCLA opened a pretty cool maker space last year, so it's free to use for anyone in engineering. So it has a lot of these kind of gizmos. So you can like, if during your project you need to go and use it. There is no reason now to have prototypes with wires hanging and all. You can make a pretty polished, almost like a product, and perhaps even productize it if it's successful. Besides that, besides kind of doing it in-house in these places, there are also companies now which enable this thing. So firstly, there are companies like Adafruit and all, where you can buy modules. Okay, so the idea is that sometimes these chips and all are very hard to work with because they may have very fine pins and all, and you can't really solder. But there are companies like Adafruit and SparkFun and all, which sell you little modules which already take care of that hard part, and then you just incorporate them into your devices. You can get open hardware designs. So you need a USB interface to put on an FPGA. Well, you'll probably find it here. Open cores, similar story. Okay, and then very easy to get PCBs and all done, very cheaply even, because what happens is the cost of making electronics, whether it's VLSI or PCB, is if the cost of preparing all the fabrication steps around it were to be done just for your design. But if we were to share, so like if instead of making a chip which just has 100 copies of your chip on the entire wafer, which will be very costly, what if we were to take 100 different designs from different customers and put them into a single wafer, then the non-recurring cost, the cost of preparing the chip mask and all, gets shared. Same thing with boards. So these kind of companies, Sunstone and all, that's the game they play. So PCBs are manufactured in like big panels, and normally it will be your PCB with multiple copies of it, which means all the machinery for fabrication and testing has to be just borne by you. But if instead you kind of take batches from a bunch of customers and then assemble them on the same panel, then each one is sharing a fraction of that non-recurring cost. So there are lots of companies like this which do it, and so suddenly PCBs and all are very affordable, very you can do. And same thing for working with materials and also. Yeah.
So apart from FPGAs, is there any other platform, more power efficient platform for implementing processor boards?
Great point. So there are some companies which do offer even the ability to make your silicon in the same manner. They call it what is called as shuttle runs, but these are probably going to be tiny chips. So if you okay, but I mean, I recall some time ago there were things which were even in a few $100 range for really tiny chips. So you could certainly do it. There are also in between things. So FPGAs are entirely programmed at your end. There are also things called gate arrays, which are partially fabricated, and the remaining things are done. But the concept remains the same. You're trying to share across many designs. When chips are made here, by faculty who work in that space, typically what happens is that companies donate them a corner of a chip or something like that, and therefore they are very affordable. But obviously that cannot do as a ordinary second. So okay, so upshot of all of this, so I think I've tried to summarize what I think are some of the foundational issues that exist in embedded computing. So certainly the platforms themselves, connectivity at all scales, both kind of this last inches and meters to last mile to kind of planetary scale, power, energy, all sort of things related around time. How does a system know what time it is? How does it synchronize with others? How does it do things in a timely manner? Location, and more broadly, other types of physical context, intelligence, broadly speaking, security, privacy, human interaction of various forms, all these kind of things. And what this course is intended to is to kind of give you a broad brush thing into some of these topics. There are deeper dive courses on which, for example, over some cycle over multiple years, I teach a course on power energy, I teach a course on security, privacy, and I'm going to be introducing a new course on AI for IoT, so edge intelligence. And then Professor Anthony Chen is teaching a course which is focused on this part, and I guess it's right before this course. Any of you taking that? Yeah, that's okay. And then Ankur Mehta teaches a course focused on robotics, right? So there's a whole sequence of, and Professor Bill Kaiser teaches a course on health. So that's kind of on the, he kind of cuts across, but in context of health. And I guess you can say Professor Mehta's course cuts across in context of robotics. So we have, I guess, 6 or 7 courses kind of dancing around these topics. And there's an undergrad course also. So, okay, so course logistics. We're going to have assignments, a topic survey. So this is one way for me to make more room for lectures. I used to have in-class presentations. This year I'm kind of switching to, you basically survey a topic out of a list I provide or which you get approval for, and you create a Wikipedia style website in effect after surveying this thing. So surveying that topic, and then a project, which is kind of the big component of the course, ideally done in a team, 2 to 3 people, no more, preferably. And kind of the idea here is to, you can decide what flavor, but most people do some sort of a design oriented thing or some cool application, but kind of designing a new platform or a new software thing and all are also perfectly fair game. Usually they end up with something which is demonstrable, but not always. So the final component of this thing is a report and a presentation with a demo, and I'm going to talk more about this. So these are 3 components. Assignments going to be a few, 3 to 4, individual for the most part. Grading algorithms. So unfortunately, a lot of things like projects and topic surveys and all, right? I mean, these kind of things, they're highly subjective in a way. Okay, it's very hard to give you like you have 89 and someone has 87. So what I do is I grade them on a letter grade basis. So basically, my philosophy is A means if it's a question, it's basically correct, or if it's something subjective, it's high quality. Okay. B, some flaws, acceptable. C, significant flaws, below average quality. D, mostly incorrect, unacceptable quality. And F, you did not even make any serious attempt. Okay, so that's the basic idea. And then I sort of convert them into their usual numeric interpretation. I do a plus minus around them, so it's finer grained than this. So like A plus would be, I mean, every year I see some A pluses, so it's not something super rare. Okay, so course project, it's your opportunity to dig deeper into something fun. Aim for something concrete and tangible, even if minor. Realistically speaking, while it's a 10-week quarter, you really have like 5 to 6 weeks of actual work on the project, because by the time you have defined the project and all, that's all you have left. And that is in the optimistic setting that you actually make use of it. A lot of students wait until week number 9 and then they decide too late, they drop the course. So UCLA lets you drop the course until week 10, interestingly. So you can shop for your grade, right? So anyway, I will provide some project topics as exemplars, but ultimately it's your responsibility. So begin a conversation with me. Oftentimes students, particularly application-oriented projects, people have some strong sort of likes, dislikes and all. So you can read the slide in depth on your own. Project timeline, this is what I kind of suggest. There are some hard milestones in it and some are softer, right? Okay, so Friday of week 3, project topic, proposal abstract and all. If you don't submit by then, you're not going to lose any points, but directly, but there is still some grade associated with it. Okay, so a little bit slack is okay, but not a lot. Friday, week 4, a detailed proposal with relevant literature. So read it. Week 7, 8, we'll have this is I have not decided the precise date because I need to check my travel schedule a little bit. But we'll have an in-class 5 to 10 minute presentation by each project team with preliminary design or results, as the case may be. Then we are going to use the final exam slot for lightning project presentations. Fortunately, our room is isolated and our final exam slot is 6 p.m. to 9 p.m. or something like that. So we'll just have pizza and presentations, I guess. And then by the end of the finals week, a longer full-fledged YouTube video presentation plus demo. And believe it, I do watch them, okay, or at least fast forward to relevant, interesting pieces, and a project report with the slides and stuff like that. Okay, so that's the project stuff. The grades are splitted this way: project proposal, so that's the first 2 weeks of week 3, week 4, 20% that midterm report when you are standing up in the class. There's 20%, and the rest is really split between quality of work, effort, oral presentation and demo, and the final project report. Okay, course on the web. Actually, I'm told that I should remove this, not used in this course, because apparently the university requires me to use it. So let me remove it. Okay, so I'm sure you're all familiar with CCLE. It's pretty archaic in my opinion, but I'm told that we have that all class-wide announcements must be made there. So I'm going to make them there as well. But if you go there and look at the class resources thing, it actually takes you to the place I post the lectures and all on Piazza. How many of you actually prefer CCLE over Piazza? No one cares? Okay, that's good to know. But anyway, I will still post. I don't want to get into trouble. But Piazza would be the primary mechanism. So the other thing I was told was, in previous years, I would just put the registrar provided email list on Piazza, and a lot of you already have accounts there, so it will automatically enroll you. This year, I'm told that I have to give you the choice of what email you wish to use. So therefore, we have given you the URL and the X code. So you have to sign up using whatever email you like to use. I think the theory is that your email is a private, privacy-sensitive piece of information, so I should not be entering it. You have to enter it. Anyway, so those are the details. I think Piazza does allow for much more easier student-initiated communication and all, so I'll leave it like that. The announcements which have to do with some time-sensitive deadline and all, I'll post in both places. Okay. Course on the web. So one thing, I don't know if you noticed at the beginning, there was a countdown timer 3, 2, 1. So I actually record these lectures. It's no camera recording. Your sound may get recorded. So if you don't want sound, don't ask questions. But the slides and my sound does get recorded, and I post them on YouTube after I convert it to the necessary format. But don't bank on it. This is not a promise that I can make, unfortunately. There are snafus occasionally, so it's a purely best effort thing, and certainly don't misuse it in the sense that stop attending, because then I will stop recording. But it's just in case you miss something or you want to go back and recheck, then it's going to be there. Let's see. For projects, actually, one thing which I had there was that all project websites would be in the form of a project on GitHub and with the associated GitHub repo. You can keep it private and share just with me, or if you choose to make it public, either way is fine. No textbook. Some of the instructions that we'll provide will basically assume that you have I guess they're most polished for Mac, simply because I use Mac, but we try to check it out on Windows and to some extent Linux as well. So I guess the thing that we don't support is Chromebooks and those kind of things. Unfortunately, it's very hard to get things running there. And also, if you're using, I think a lot of stuff if is really for Linux, and if you are doing it under virtualization, it can be pretty slow. But fortunately, I think Docker containers are actually pretty good on both the platforms, and Windows 10 has a good Linux subsystem. So for some version of Windows 10 at least, I don't use it, but again, I'm told it's pretty good. So a lot of issues we used to face early on are not so much. And also the main platform I like to use, the Embed OS, has a good online compiler also. So they do provide a command line chain, but it's also online. So it would be good for you to have a smartphone and know how to program it. I think generally Android is more friendly. So the smartphone serves two types of purposes for you, particularly for projects. They're loaded with sensors, right? I mean, so for you can think of them as really an embedded system plus a phone attached to it. So you can a lot of projects involving sensors and all you can do around the smartphones to help in this process, and I guess partly also to accommodate a travel related thing. Next lecture is going to be my postdoc Luis Garcia, who's going to walk you through Android architecture and how to write Android apps which make use of sensor data and all. It's purely intended as a useful thing for you to know so that you can make use of it in your projects and stuff like that. So I kind of realize embedded systems are not, smartphones are not exactly truly embedded systems that in the strict sense, but they are very powerful and useful components in this ecosystem. We'll only talk about Android, but iOS is also pretty good, and every year I have some students who already, who have iPhones and know how to program it or want to learn how to program it. You can do that as well. We can try to assist you. I unfortunately currently do not have any student who in my lab who knows iOS programming, but actually no, I do, Joseph Noor. So we can try to help you there a little bit as well. Okay, but the lecture will only cover Android. So basically, kind of when it comes to the hardware platforms that you would need to work with in this course, both for assignments, although for assignments I'm exploring a simulation pathway also, as well as projects, essentially boil down to some sort of embedded device, some sort of a gateway device, and then making use of cloud services, many of them which are available for free. Now, I've tried many different models on these things, and the problem out here is the following. The devices here keep changing every year, and the thing is, when they change, unfortunately, the old ones go out of stock. So I can't continually kind of deal with that mess. So I kind of, and I don't want you to waste your money either. So I'm still kind of deciding what is in stock and all, and I'll probably buy a bunch of them. Then you can check it out against a deposit, with the deal being you return it in fully functional condition. But of course, you're welcome to buy them up. So I'll give you for this thing between smartphone, and I have a supply of Raspberry Pi Zeros, which again you check out, they're pretty cheap, like $10. So okay. A whole bunch of platforms. Last year we used this platform which looks like a smartwatch and all. Unfortunately, it's a very fragile device, so I'm not planning to use it, although it's available for projects, but wasn't a good choice for, it's called Hexaware. It has a whole bunch of sensors and all, but unfortunately, it was a bit of a pain to work with. Raspberry Pis are great. If you already have Raspberry Pis, that's great. If not, like I said, I have a supply of Raspberry Pi Zeros. Cheating and plagiarism, basic thing is, if it's an individual assignment, you need to do it individually. If it's a team thing, you need to do it within the team. Any cross-team or cross-individual thing has to be something which you check with me, and should be done openly on Piazza. Okay. Let's see. The another issue that I face with it is that in team projects, occasionally there are issues where someone will complain, my partner didn't do the work and all. So to cope with that, I would have separate from the project report. Each team member has to submit an independent short report on what each team member did. Okay, so and then I will basically try to assess from that. Ultimately, working in a team is something that you just have to learn how to do with when you face team working in your professional lives as well. Okay, cheating and plagiarism. So basically, yeah, you can read, but basically you get if you violate any expectations, and basically gets reported to the university. Impact of travel schedules. So unfortunately, I always do end up having some travel conflicts or other. So I try to make I make all of them up, and we do it in one of three ways. Substitute or guest lectures. So some of these things like teaching you how to use Android and all, they are my students or postdocs do a much better job in any case. So I try to sort of arrange those pre-recorded lectures, because since I record, so I can do that, and then perhaps make up lectures. So you'll have all the lectures, but might be one of these. The first conflict is actually this Thursday. So this is where we have the Android lecture by Louis. I think he will send, he's also added as a co-instructor on Piazza. I think he's going to send out some note, but basically I think if you can bring your laptop and download Android Studio, I think then you can follow along some things even in the class. Okay, so that might be useful. And if you have a Android phone, great. But even otherwise, there's a emulator which comes with part of Android Studio. So you can, if you have an iPhone, no problem, you can just work with the emulator. Okay, any questions?
For Piazza, I know like it gives you the feature to contact the instructor. Is that your preferred way?
That's my preferred way. Okay. Because then I get a notification on my phone and immediately respond to the Piazza app. So it's a lot easier. And by the way, I have enabled, you can maintain anonymity and all, and it's perfectly fine with me. Just don't misuse it in the sense that you should not post anything which is offensive. But you can choose to mail to the class or to me anonymously, and that's perfectly fine. Any other questions? Okay, so before I move to the main lecture, just to get a sense of who's here, I want you to fill out this attendance form by the end of, like shortly after the end of the lecture. Make sure you have filled it out. It just asks for your name and your student ID and what your current status is. Okay, like are you just auditing and stuff like that. Okay.
For the username, you have to put the G or something. For the Google form, sometimes it's like
Did everyone capture the URL? No? Someone still? Okay. Anyone still needs it up there? Okay. Let's see one. For people in the back row, is the QR code big enough? Okay, I'll move to the
With the enrollment request form, is it a deadline to submit?
I will, ideally, if you can do it by Thursday or so that I can assign it over Friday or the weekend. Okay. Okay, so the first main lecture is to talk about some of the issues around the hardware platforms, and in particular focusing on hardware platforms on those resource constrained edge devices. Okay. Of course, even things like cars and planes and all have very much the same thing. It's just that they have a whole bunch of them and they are networked. Okay, so very similar issues. So if I generically look at an embedded system platform, it would have some way of interacting with the physical world and the human world. So sensors, actuators, and human interfaces. And actually, the slide is a bit misleading in a way because we often interact with humans also using sensors and actuators, right? I mean, measuring physiological signals and stuff like that. So humans are part of it also. Some sort of computation and storage sort of substrate. And there are a variety of choices that exist. I mean, of course, there are processors, but there are also specialized processors, so specialized things like single processors, FPGAs, custom chips, application-specific chips, and then again various kind of memory and storage things also. And sometimes these things are on the same chip, sometimes they are kind of spread across multiple chips. Network interfaces, oftentimes it's radio, sometimes it could be Ethernet or some other wired interface, and then I/O interfaces are for talking with off-chip sensors and all. So this is where you have things like serial bus and I2C and SPI and USB and those kind of things. And again, the boundary sometimes gets muddy because you can run network protocols over some of these I/O interfaces also. So at the end of the day, it's just sending bits over something. And then a very crucial but often forgotten part is the power subsystem, which would have some sort of a supply of power supply, battery, energy harvester, like from motion or solar cell or something like that, some sort of energy storage thing, capacitor, rechargeable battery, and regulator, which cleans up the power, cleans up the voltage before supplying it to rest of the system. So in a way, all these things are areas of sort of significant investigation on their own, but this is kind of the generic. And then when it comes time for implementing the computation part, as I mentioned, there are all those choices that existed inside the bubble. So one thing you could do is where you say, okay, fine, I'm going to make my own chip, okay, and or implement a whole system on a dedicated chip. And you can certainly do it. ASIC basically says all the way from, I mean, every transistor belongs to you. FPGAs are chips which you can think of them as they have a whole bunch of transistors on them and wires, and you can program the connectivity between the transistors or the gates. And so they stand for field programmable gate arrays. They are arrays of gates which are programmable in the field. So it all makes hardware seem a little bit like software. You can very rapidly change them. They come in a couple of varieties. One where it's literally like a memory. You just write into the memory and it changes the hardware behavior. And others are like little fuses or something. So you have to apply a high voltage and kind of program them. But the first variety are far more common. You literally, like I said, very rapidly kind of change their behavior, rewire the transistors. Oftentimes, they, in addition to just transistors and all, they already come with bigger modules. So like you will see FPGAs which may already have a processor on them. So they will have a processor surrounded by some memory and surrounded by some gates which are uncommitted. So you can create some pretty interesting things. Some of them even have analog components like op amps and all. And so you can interface them with sensors and or A to D converter, D to A converters. You can create your own custom boards. this probably is more accessible for hobbyist or sort of much of academic research. So you can buy off-the-shelf components, COTS stands for common off-the-shelf, and then you can create your own custom boards, and this is much lower cost. For a few $100s, you can get or certainly, let's say, order of $1,000, you can get sort of pretty interesting stuff done. And then you can go one level up. You can just create a custom system. So now you just buy boards and plug them into chassis. So there are standard in this space. There are standards exist for chassis also. So essentially, they have a backplane with slots, and so like CPCI stands for compact PCI. So it's a industrial standard where they kind of look like these. So essentially, chassis with slots, and people make all sort of boards, CPU boards, A to D converter board, motor control boards, all kind of things. You can buy, plug them, you can create your own system. As you can see, I mean, obviously, things are a lot more efficient at the top and becomes a lot less efficient. And finally, in many embedded systems, people just use a ruggedized PC or a ruggedized smartphone, weatherproofed and stuff like that. So a lot of, like, for example, the autonomous driving system in a car may just be a PC, or certainly like sales terminals and stores and all. They are all just standard PCs. So there are embedded version of Windows and all, which kind of, and embedded Linuxes, which kind of cater to this climate also. These choices have a tremendous impact. So one way of thinking about them is that on one hand, we have things like those PCs and all, which are basically just using microprocessors. And then you can have processors which are specialized for, so like for graphics or for signal processing, and nowadays for AI, machine learning also. Then another category of processors where you get to choose the instructions. So these things also exist. There are companies which basically take care of most of the processor, but you can customize the instruction set. And then increasing customization all the way down to your own silicon. And one way of thinking about it is, if I think in terms of speed, then I get more performance down here, obviously, right? Because processors are they're like elephants. They can do, they can do a lot of things, but are very heavyweight, right? Just to do an AND instruction would be just an AND gate out here, but it would be the whole sequence of like tens of thousands of transistors potentially engaged in doing that AND instruction out here. So speed, sort of, you'll expect better. Power, you will expect, again, this side to be better, so power goes up or energy goes up out here, less efficient, more efficient. A good rule of thumb is that every degree, every time you specialize, so going from microprocessors to FPGAs, a 10x, and going from FPGAs to ASICs, another 10x loss in performance or power efficiency. Cost. What do you think about cost? So which one would be cheaper? ASIC in large production, and if I'm making only one off, then up here, right? And so the issue, so cost becomes is a more nuanced thing, and the reason basically is that the total product cost consists of both that one-time cost, which is if you're making the chip, the mask needs to be made. If you're making the PCB, someone has to again assemble all the infrastructure, testing strategies and all. So there is a fixed non-recurring cost, and then there is a cost which is per part. And so overall cost is a summation of the two. And so the fixed cost include all other things, purchasing the PCB. If you're designing a chip, well, you have to get the EDA tools, and they themselves are pretty expensive, or a PCB design tool. Whereas other things are kind of a function with scale as n. For chips, there are also wafer cost and stuff like that. But long story short, both chips and PCBs have both these components, and therefore, if you look at sort of the overall structure, so like FPGAs, fixed cost, and sort of different kind of devices are going to have different fixed cost structure, but cost per part might differ considerably. When you are buying a microprocessor from Intel, then Intel sells hundreds of millions of those devices, so the fixed cost is shared among all those. So even though it's a behemoth, like a few billion transistors, but so you're paying the cost of those processors. So anyone knows how much a good Intel processor costs nowadays? Okay, so those are relatively low end. You can buy processors all the way up to a few $1,000s. Okay, so that's the scale. What about FPGAs? So they go from a few dollars to $20,000. Okay, the high end. Okay, so all over the map. Okay, so depends on the size of the chip and all. But it's this complex interplay which happens. So back to our figure, at high volume, the microprocessor solution is worse, because if you had made your own chip, you would have been better off, because the fixed cost would have disappeared and you have a more efficient design. At low volumes, you are better off being somewhere out here, because you are then riding the fixed cost curve, sharing the fixed cost with a whole bunch of other users. There's an additional factor also, which is it's not simply the cost. Ultimately, if you're a company, you're in the business of making profit. And there is also cost associated with the delay in a product, right? So if I can get the product out to market earlier, then I'm going to capture more of the market and more of the share. So you also have to take into account that lost sale part of it. So sometimes you would see that a camera might come out using an FPGA initially and then later on transition to an ASIC, just so that you can come out early. So that's an additional factor one must consider, which is if you are late, then that could permanently, that this not only lost sales, it can also permanently relegate you to second to market, and so a lower market share. Now, having said that, a lot of systems that we see nowadays are basically microcontrollers based with accelerators attached to them. So sort of people try to find the sweet spot. They say, let's have sort of best of both the things. So you have an MCU, which is basically kind of a little computer which has a CPU, a microprocessor if you may, but on the same chip it has ROM, RAM and peripherals also. So sort of companies find different configurations. So like they will take a CPU core, let's say something from ARM, and then create different MCUs, kind of a whole family of MCUs with different sizes of ROM, RAM and different choices of peripherals. And then nowadays they increasingly go further also, and you may also have some accelerators on it, like a crypto accelerator or a graphics accelerator or a signal processor or nowadays neural accelerators. Okay, so these kind of things. So they all so this model of a processor plus peripherals plus memory plus an accelerator, which is specific to a particular domain, is very common. So majority of the CPUs nowadays are sold indeed as part of these MCUs. So I mean far more than kind of standalone microprocessors. Of course, the costs here are very different. How much do you think these things cost?
Few dollars.
Pennies often. Okay, I mean so in high volumes they might just be a few tens of cents, a few dollars. I think the high end may still be a few tens of dollars out here, but common price point here. So this is a large volume, super large volume, very thin margin, low cost regime. I guess as I mentioned earlier, it's very ARM is the main sort of dominant force out here, and the model there is ARM designs the processor, and then other companies take that design and implement them on silicon. So ARM designs this, and it also kind of designs some of this stuff and all. But then there are companies like ST Microelectronics and NXP and these kind of companies, or Qualcomm or Samsung, who take these chips and take these cores, and then they create their own processors around them. So like Samsung has has Exynos, and Qualcomm has Snapdragon. Now I didn't mention Apple in this thing. Why? They still use ARM, but they don't take ARM's designs. So what Apple is what is called as a architecture licensee. So they have licensed the ARM architecture. So they can create their own implementations of the ARM instruction set architecture. Qualcomm and Samsung used to be like that, but not anymore, mostly because it's a lot more expensive. So now Exynos and Snapdragon, they basically use the cores that ARM designs, and then they put their magic elsewhere. Okay, and of course, these chips don't have a single core; they have many cores. Like if you look at, I'm sure these modern mobile chips have 8 cores or 12 cores and all. Okay, and then a whole bunch of other hidden cores. But Apple is an architecture licensee, which is why they have highly optimized implementations and all. Now, again, it all boils down to economics. Apple can afford to do it because it makes kind of a bunch of devices which are using the same processor. So for them, that extra cost and the power efficiencies they gain out of it is worth it. Okay, so you also have other contenders out here. Of course, Intel Atom. There are also companies like Atmel, Texas Instruments, who make processor families, which are PIC microcontroller, the old Intel 8051 series things. So those are also very common. But I think the more interesting new entry is the RISC-V that I mentioned earlier, open source design. You can support it on a lot of FPGA boards, or if you want to spin your own silicon, you can do it. It's pretty tiny, efficient, supported by, there are compilers and operating systems and stuff like that. So it's a pretty cool development, and actually there was a bit of a back and forth. I guess, as you might imagine, there is a bit of concern from ARM, obviously, around the development of RISC-V. So initially, I think they took some stance which didn't go very well, but eventually ARM, as a consequence of this, opened up its processors. So ARM has a whole bunch of like the M series, A series. So some years ago, they had opened up their lowest end processor, which is called M0, which is the simplest, tiniest microcontroller. But they didn't open up anything else. But then RISC-V came, and then of course competition is good. So now ARM has opened up its more advanced processors also. So now I guess things are a little bit more even, but still RISC-V, meanwhile, sort of there's a big community which has developed around it, and you don't have to worry about any IP, copyright, those kind of issues. And also it's as you might imagine, like when it comes to things like let's say tariffs and licensing across countries and all, RISC-V kind of things become very attractive. They're open source for anyone to design anything around them. So there's a lot of action around this in other countries, because they can you basically have a completely open compute stack at this point if you wish to go down that route. Back to microcontrollers. So microprocessor is basically just the CPU. Okay, so it has the control logic, registers, and the arithmetic logic unit. And then microcontroller is all of this together with ROM, RAM, and I/O. So it's like an entire computer other than the keyboards and stuff like that. And so it's a single chip computer, and like I said, many companies make it. And Texas Instruments processor cores are very well regarded for their low power consumption, but ARM is the dominating force, and RISC-V is kind of this new open source thing that has emerged. And then there are kind of these smaller players like Atmel and all. Okay, so when you buy an MCU, you basically buy a chip which has all the stuff in it which used to be previously separate chips, right? So if you currently, when you have a desktop, laptop and all, then it obviously has it has a separate microprocessor chip, and memory and all are separate chips on the motherboard. But with an MCU, everything is on a single chip. So you literally can just design a board with just that and a power supply and anything else that you need to interact with, and good to go. Oftentimes, these peripherals include sensors and all also on it, because, and in fact, now it's even possible to make clocks on the same chip. So, and you can even put batteries, there are things called thin film batteries, and also if you really want to be aggressive, almost everything about a complete system you can put on a single chip, other than you have to supply power to it. You can have a radio. So I guess sometime I think, is it possible to have a no pin chip? So you could imagine that you could have some sort of an energy harvesting thing inside the chip, and in that case the chip could be without any I/O of any form, and we kind of in a way sort of driven towards it, that this heavy integration that has been happening. What also has happened is that in addition to putting the processor core, they often put basically little FPGAs kind of things next to that processor core. So you have these chips now which are called as programmable system on chips, where in it there's a processor core, memory, peripherals, and then some amount of digital or analog logic which you can program. So digital logic may basically be some gates and some ability to rewire them, and then some stuff which is necessary for analog circuits like A to D converters or amplifiers and stuff like that. So magic in whether it's digital or analog, the magic is the rewiring the thing. So basically what happens is that the wire gets replaced by some way of either cutting the wire open or making it close. So there are two ways of doing it. Imagine that the wire had a little fuse. If you blow the fuse, the wire gets disconnected. So I can cut open a wire that way. Alternatively, I can put a transistor out there, and by turning the transistor on and off, depending upon the content of a memory which is driving the transistor, again I can open or close the wire. Okay, so open or short, sorry. The wire is either open or short. Okay, so I can basically control the connectivity. And that's what happens in these. It comes at a cost because my wires are no longer as efficient. So they burn more energy. So FPGAs are going to be slower and burn more energy, but still much better than doing the computation on the processor core. So these kind of chips, so there's a company called Cypress which makes programmable SoCs, but they're not the only one. There are a lot of other companies which make such chips. When it comes to these microcontrollers, there are immense diversity of things that exist in terms of how many bits they have. There are 4-bit microcontrollers all the way to 64 actually. What kind of memory they have, do they support external memory or not, what kind of instruction set they have. Like I said, ARM and RISC-V dominate, but there are still kind of more traditional CISC architectures, what kind of memory architectures they have internally, and then I've listed kind of a whole bunch of manufacturing families that exist. So this is again high volume thing. Oftentimes, once your part gets inserted into a product line, then if something like a car, if you think about it, the car would have a lifespan of 15-20 years. So once GM or Ford or BMW or someone buys into something, they're not going to replace it very easily. But some of it has begun to change. I mean, for example, earlier this year, Tesla had made the big splash that how they created a new chip for doing the AI processing on their cars. So suddenly car companies are designing kind of the high-end chips also. So instead of using the NVIDIA chips, they decided to go their own route and made lots of claims about its power. ARM is dominant, as I mentioned, but RISC-V is kind of an interesting thing. So just to give you an example of MCUs from just one vendor. So ST Microelectronics is one of the big players in terms of actually selling the chips. based around ARM. So they have, for example, a high performance end, a mid performance end, and wireless and automotive. Okay, the point is there are a whole bunch of these specialized segments they create, and what's happening really there is there's the peripherals and the memory and all that sort of get changed. So, for example, they have this range of ultra low power MCUs. Okay. And you can buy within that family a whole bunch of these things. So oftentimes you're designing, part of the game boils down to you have to kind of figure out what does your application need, will the code fit into this thing, and you kind of iterate between software and hardware. This is because it's very cost sensitive, so you don't simply make the hardware and then go and run the software on it. You kind of go hand in hand. Every byte matters in some of these systems. Now, as you can imagine, so there are two reasons why. Dominant reason why there's so much attention to memory is because when it comes to power consumption, RAM is extremely power hungry. Okay, so why is that? So there are two types of RAMs, right? There is DRAMs and SRAMs. DRAMs use a single transistor to store the value, and if you are reading or writing it frequently enough, you don't need to do anything, otherwise you need to refresh it. But DRAMs are slow. Okay, if your processor is running at a few hundred megahertz, DRAMs are going to take many cycles to do it. So in standard computers, we take care of that speed mismatch by doing what? Caches. Now, what kind of memories are caches? SRAMs, right? They are faster, but they take more transistors, 6 transistors, typical configuration. In MCUs, everything is an SRAM, and then you have flash memory, okay, so to store the program. But you can't have a whole lot of SRAM. SRAM is area hungry and power hungry. So what ends up happening now is that the amount of SRAMs on these chips is in kilobytes. Okay, will be like let's say order of 100 kilobyte max. That would be luxury. Oftentimes it's 4, 10. Okay, so if you I think we have not even listed the amount of RAM out here, but the point is, for reasons of power alone, they are fairly small. So the programs here are highly optimized. Also, on our regular computers, we have huge amounts of storage, huge amounts of either a SSD or hard drive. So using virtual memory, anyone knows what virtual memory is, right? I mean, we basically give the illusion of a large address space and then back it up on the hard drive, on the storage. We can't do that here either, because even our virtual memory is pretty tiny. The storage is pretty tiny, a few megabytes of flash. So a lot of things that we are used to on a standard computer don't work out here. So the mindset here, every data structure and all matters. You have to kind of count things. You have to make sure your stack will not overflow. You have to make sure that if you are dynamically allocating a data structure, you will actually have space for it. And there are no protections. On your regular computer, if it overflows, just that process dies. Here, the whole thing will crash. So the mindset on how you program these things changes. This is often called as bare metal programming, because you are literally kind of working right close to the hardware. So I'm sure if you have programmed Arduino and all, you have been exposed to some of it, but there are considerable safety and resilience issues and all that kind of arise out here. So this is just wanted to show the rich variety. When you're looking at these MCUs, you have to look at performance. There are indeed MCUs that go up to gigahertz type range, power, actually nanowatts to watts, program memory, data memory, I/O, peripherals, internal functions, and all sort of other considerations. So it's a very rich mix, and just a single vendor will probably offer a few hundreds, if not more, sort of configurations of their MCUs, and just selecting them becomes a interesting sort of initial design consideration. So a typical MCU-based platform then might look like the MCU. That's kind of like the single chip. And sometimes these MCUs even have a radio built in. You can find these kind of MCUs also. And then you might have some connectors and all. So you can kind of make simple embedded systems, which are, if you find the right MCU, sort of pretty easily, and then you surround them with some power supply circuit and all also. Yeah, I'm going to stop out here. We okay, we have 30 seconds. So I've shown that Hexaware platform earlier. So just wanted to show like what exists in a typical platform like this. So it has actually two MCUs in it. They have an MCU which is dedicated entirely to Bluetooth, and then there is a main MCU which is sitting out here, okay, under the screen. So there is a little LCD or a little OLED, and it's under that. Okay, so this is the main application processor, and then the Bluetooth protocols are complicated enough that there is a separate processor with its own firmware and chip for it. In this one, when you write applications and program and all, it's the main processor that you work with. So you see the same thing in smartphones and all, or even a single mobile chip from like Snapdragon chip. Besides those application cores, there are a whole bunch of other processors doing special things, something with Bluetooth, something with sensors. A concept which has emerged in recent years is sensor hub. Like, for example, Apple some time ago introduced something called motion processor. Now, motion processor basically took the motion sensor data and continuously computed what were you doing, like how many steps, are you sitting, walking, stuff like that. But actually, it was nothing other than a Cortex-M processor, and they were running a specialized software. It was not visible to you as a programmer, but it still existed. So modern systems have a lot of these hidden processors, and then these application processors. And that's kind of the architecture out here. So, okay, I've gone over time. So I'll see you guys on Monday. Thursday lecture is on Android. So, sorry, Wednesday. The Android lecture is Wednesday.